here's the last basic part of this torsion stuff before we start talking about static dynamics. I want to talk a little bit about J. You know, in your text, it doesn't really go over it that well, but I think it's appendix C. No, appendix A. If you look at appendix A in the back of the book, it goes over all these sort of geometric issues with computing J, some of which you actually covered in statics, okay? But let me just review some of that stuff because I know some of you get things. Let's just talk about J, and in general, really these area moments. These are these integrals. They're going to pop up a lot in this class. J, remember, is the second polar area. So J, which is the integral over the cross-sectional area of the radius squared. This is what we call the second polar area moment. So it's not a bad idea to go over some of the tricks of where this has come from. And again, we'll see them when we talk about bending, okay? And shear bending as well. Shear. All right. So let's just talk about these moments, this concept of zero moment, first moment, second moment. Right? I mentioned this in one of the videos. I think when I did the torsion equation. We've got basically, let's just talk about Cartesian coordinates. So let's say we have some shape here, right? And let's call this the x-axis. So we know that the area is the integral over the area, the differential area. That is the area. So you can imagine, like, let's just consider y. This is like sticking a y to 0 power because y is 0 to 1, right? So this would be an example of 0. Area because it's differential area. When you do dynamics, this is not dA, but it's dN, and that leads you to a zero mass moment, okay? Inertia. All right. Now, you can also imagine the first area, I'll call this Q actually later on, where it would be y to the first, because y would be that first area. See this when we talk about finding centroid. So, for example, let's say you want to find the location of the centroid of this shape, right? And it's denoted by this distance here, this sort of y prime. That's at least the distance to the y center, right? You can also do x prime. So, for example, y prime, those remember, is the integral over the area of y dA over the area. So you can see here, this, in the numerator, that's that first area. And this bottom one here is the zero area, right? So here's a first area moment. It comes in when we talk about finding centroids. So it's moment arm is to the first power. Here the moment arm is to the 0 power, right? This is y as sort of a moment arm, right? Okay. Now, when we do torsion, what pops out is the second area. So you can do a second area. When we do bending, we'll actually call it secondary I. Y squared, that's the second area. All right, so it's the second moment because it's y squared. Area because it's dA. Now, in bending, we'll use this, it's called I. Okay? So, but in our case, it looks a lot like this, but we're not using y, we're using the radius, rho squared, which actually is x squared plus y squared. So that's what makes this polar area. So this is J, by definition, the integral of the area, rho squared. That's the second polar polar second area moment? Not polar, right? It was first or second, but anyway, that's what you get. And so you can see actually, J, if I write this as x squared plus y squared, this becomes x squared plus y squared dA, because that's rho squared, which is x squared dA plus y squared dA. See, this is the two Cartesian second area lines. I, y, here, I. Okay? All right, so we'll do that. That's what you get. So that's where the name comes from. All right, so let's talk about computing it. So you can compute it for a variety of geometries. Most often, in this case, we're going to be talking about J for circular cross sections. We probably won't get to it too much in this class, but actually, really, this theory is only valid for circular cross sections. Right? Even we will use it for hollow circular cross sections, but it actually is a bit of a simplification. You know, even as you get to very thin circular cross sections, where maybe the outer wall is very thin wall tube. You know, all this theory we've done with TC on J actually starts to break down, and so I guess what I'm saying is like tau equals TC on J type of concept, right? This is good for circular cross sections. Really, actually, theoretically, only good for solid circular cross sections. Sometimes we can deal with hollow ones where the wall is relatively thick. As soon as the wall starts to become thin, it starts to break down. You can still use it, but it's not ideal. And actually, there's sections in the text, chapter 5, that discuss this. You can use it for square and rectangular cross sections, but it starts to break down a little bit. Actually, what you find is actually the maximum shear stresses occur here, not in the corners. And then lastly, thin wall, closed sections, it varies quite a bit. You really can't use it for this. Use this for somewhat. Both this situation and this situation. Good for this. Everything we're doing is good for this. When you start getting into situations, you can use it a little bit. This one you really shouldn't use it. Definitely, you have like open, thin wall cross sections. Definitely, shear stress distribution is quite a bit different than this pinwheel polar distribution we deal with. Okay, so although you can actually compute J for those types of shapes, and the book does some of those things, I think it even does it for a equilateral triangle. You know, you have to use those with some amount of suspicion. The theory is really, well, it's only really good for a solid circular cross section, although it's actually not bad for a hollow, thicker wall cross section. As the wall becomes thinner, or you get non-circular sections, it starts to become a little suspicious as to what, how valid, you know, this TC on J is. Okay? All right. Let's compute this. So it's mostly valid for solid circular cross section. Do it. This is really just algebra again. So here's our solid circular cross section. It has an outer radius of C. Right? So we know this is supposed to be a differential area, A. That's some distance rho from the center. I really drew that for you. J, integral over the area, rho squared to A. So kind of blow up that. dA looks like this. So this is rho, okay? This differential area, we can write this as this is 0. This distance here is rho theta, so dA is rho theta rdr. Right, that's the differential area. So this, breaking up the integral, is rho 0 to outer radius c. Okay? All right, so this first integral is really easy to deal with because there's no theta dependency in here. So this just becomes rho theta from 0 to 2 pi, or in other words, just 2 pi rho. All right, so now we've got J is equal to the integral from 0 to c of 2 pi, and I forgot to put it here. That's for the initial rho square. So we actually have a rho cube here. This is rho cube. So 2 pi rho cube d rho. Okay? Sorry about that. Rho cube. Rho cube. All right. So here's our rho squared. I put the differential area. I put another rho. Right? Rho d theta rho. So this rho squared times rho gives me rho cubed. The first integral puts 2 pi out. Okay? So now we just integrate with respect to rho. So now J is equal to 2 pi. This is rho cubed, so its antiderivative is 1/4 rho to the 4th, integrating from 0 to c. This becomes 2 down here, so this now becomes pi c to the 4th over 2. And there you get the dimensions of length of the 4, right? Now, most often, you don't go to the store and buy a bolt with a 1/4 millimeter radius, right? Most engineering circular type of things are given in terms of diameter, right? So let's get this in terms of diameter. Actually, that's the way I memorize it. Although you can do this as well. The diameter is nothing more than twice the radius, obviously, right? So if you want to get this in terms of diameter, we can just put in for c d on 2, and then if we do that, c to the 4th is going to be d to the 4th on 16. Put that into here, c dot j, then going to be pi over 32 diameter. That's actually the one I have. Pi over 32 diameter 4, because most often we're given diameters, not radius. But if you like to do in terms of radii, you can do that. Right? All right. So that's that equation. Now, what about for a hollow section? Well, you could redo the integral, but actually, there's a good trick for dealing with hollow tubes. So this is the geometry we're now talking about. Can't really let the wall get too thin, as I mentioned before. So now I have a outer radius and inner radius. Okay? But really, let's deal with the diameter. So the outer diameter, that's usually what you see. All right. One way is you can do the same integral and just integrate from ci to c naught. But let's do a different approach. And actually, we use this a lot more when we do beams. This is the area that we want to do. Right? So if I break that up into two areas, outer area minus the inner area. Okay? This is the outer area, and this is the inner area, right? So that's the area formed by the inner tube that's bored out. This is the formed by the outer area. So if we look at J, and that's just the integral over the area of rho squared, yeah, right? Where this is A, right? That is my differential area A. That's what I really want to do. The area I can write as the outer area minus the inner area, right? So this is the same as forming integral over the outer area, right? As if I got J for this outer shape, minus the integral for the inner area. See, I just broke it up here, right? But I put a minus sign in because this is actually negative. Then we do that. What you can see here is this is J of the outer shape. J as if it were a solid cross section. And this is just the J of the inner cross section with the minus sign. So we'll do this also when we do bending of a few eyes. When we have cutouts, you'll take the eye from the cutout, subtract it from the outside eye, and that'll sometimes be a shortcut. So in this case, fine. So J for the hollow tube. Okay, it's J of the outer tube minus J of the cutout, the hole. So the outer J is pi, third tube, third tube. Outer diameter. That's J, right? That's the outer J. And we're going to minus the J from the inner. That would be just pi over third tube inner diameter. And then, you know, we take pi over 32 out, this just becomes pi over 32 outer diameter to the fourth minus inner diameter. That's what you get for hollow tube, right? So make sure you don't do this. You'll see this other thing. Right? That's not the same, right? The fourth power goes inside when it gets raised to the fourth thing, then you take it. It's not taking different diameter. Okay? But anyway, so we'll see this trick when we do that. Okay. Quickly, sometimes get the area moments from a composite section. Right? By and subtract. Okay? Alright, that's all I wanted to talk about today. Now, yeah, why don't we stop there? I'll talk about